Welcome to Homework Lib.
For this problem on the topic of quantum mechanics, we have an electron in a cubical box of side length L, initially in the ground state. The longest wavelength photon that is absorbed has a wavelength in A of 624 nanometers, and we want to find the side length L. The wavelength lambda is found to be 234 nanometers, which is also absorbed when the initial state is still in the ground state. We want to then find the value of n squared for the final state in the transition for which this wavelength is absorbed, where we know n squared is nx squared plus ny squared plus nz squared. We then want to find the degeneracy of this energy level. Now, the energy levels of a particle in a cubical box of length L are E, nx, ny, nz, and this is equal to nx squared plus ny squared plus nz squared times pi squared h bar squared over 2ml squared. And the longest wavelength absorbed is for the smallest energy transition, which is between the ground state 111 and the next highest state 211. The energy absorbed by the photon delta E is hc over lambda. So for the lowest energy transition, we have delta E equal to 2 squared plus 1 squared plus 1 squared minus 1 squared plus 1 squared plus 1 squared into pi squared h bar squared over 2ml squared. And this is equal to the energy of the photon delta E, which is hc over lambda, or hc over 624 nanometers. And so from here we get, by rearranging, that the side length of the box L is equal to the square root of 3 times Planck's constant h times 624 nanometers divided by 8 mc. Putting in our values, we get this to be the square root of 3 into 6.626 times 10 to the minus 34 joule seconds, which is Planck's constant, times 624 nanometers divided by 8 times 9.11 times 10 to the minus 31 kg, the mass of the electron, times the speed of light in vacuum, 3 times 10 to the power 8 meters per second. And so calculating, we get the length of the box to be 7.53 times 10 to the minus 10 meters, which is 0.753 nanometers. Next, in part B of the problem, the final state is now n, and we'll call the wavelength in part A lambda 1 and the one in part B lambda 2. So from part A, we have hc over lambda 1 equal to 3 pi squared h bar squared divided by 2ml squared. And for part B, we have hc over lambda 2 equal to n squared minus 3 into pi squared h bar squared over 2ml squared. If we divide these two equations, hc over lambda 2 over hc divided by lambda 1, we get this to be simply lambda 1 by lambda 2, which is 624 over 234, both measured in nanometers, which is n squared minus 3 over 3. And so solving, we get n squared equal to 11, and There are three possibilities: 113, 131, and 311. And so, including spin, the degeneracy is 6.